So here we're going to review the idea of limits at infinity, section 2.2 in our book. This is hopefully familiar. We can just brush the cobwebs off from last year. So we have some examples we're going to work. As x goes to infinity, we imagine that as x gets bigger and bigger, 1,000, 1,000,000, 1,000,000,000, this gets closer and closer to 0. So we say that its limit is equal to 0. In the second one, when you have 3 plus 1 over x, as x goes to infinity, the 1 over x is going to go to 0. The 3 is unaffected by what x is doing, so it's going to always be 3, and so we get that the limit is equal to 3. As x goes to infinity in a rational function where you have a polynomial over a polynomial, as x gets really, really big, the plus 1 becomes insignificant. And in the denominator, the same thing's true with the minus 3. So we direct our attention to the highest powers of x and their coefficients. So as x gets very, very large, this will look more and more like 2x over x, which will be 2. And so that will be our limit. In a similar fashion, if we have the degree of the numerator is greater than the degree of the denominator, we still direct our attention to the highest powers of x and their coefficients. So this will act more and more like x squared over 5x. We could, if you want, cancel an x, and so it'll look more and more like x equals 5. So as x gets larger and larger, we could say correctly that it goes to infinity, or probably better would be it does not exist, or maybe safer. In the next one, again, we have this time the degree of the denominator is greater than the degree of the numerator. So the higher powers of x will dominate. And so this will act more and more like 1 over x. And as x gets huge, that is going to approach 0. So we have our definition of what it means to be a horizontal asymptote. If the limit as x goes to either positive infinity or negative infinity is a finite number, then y equals that is going to be a horizontal asymptote. So we'll look at some interesting ones here, perhaps. The first one, now this is not a rational function, but we can take first the limit as x goes to positive infinity. And so as x gets really, really big, we see, well, inside that radical, that plus 1 is pretty insignificant as x goes to 100, 1,000, 1,000,000. So that will look more and more like x over the square root of x squared. And so I don't like to use equal signs there, so I'm going to say, well, that's going to act more and more like, and now here's where you have to be careful, because the square root of x squared is not actually just x, it's the absolute value of x. Now, since we're going to positive infinity, it doesn't really matter, because 1,000 over the absolute value of 1,000, 1,000,000 over the absolute value of 1,000,000 is always going to be 1, and so that's going to be our limit. And so we have y equals 1 is a horizontal asymptote to the right, since that's going to positive infinity. Now, if we take the limit as x goes to negative infinity, then we have a lot of the same reasoning that goes on. As x gets really, really big, that plus 1 is going to be insignificant, and it's going to look more and more like x over the square root of x squared. And now is where our paying attention to the details pays off, because now as x goes to negative infinity, this will go to negative 1. And so you will have a horizontal asymptote to the left of y equals negative 1. Crazy. The next one's kind of interesting more because we get another chance to, I think you can tell what the limit is just by looking at it. That is, we take the limit as x goes to infinity. But it's kind of a nice application. I mean, we can think of it nicely in terms of the sandwich theorem or the squeeze theorem again. So if we consider the limit as x goes to infinity, so we can see again that sine x over x because the biggest sign can never be is 1, and the smallest it can never be is -1, then we can take the limit as x goes to infinity of that, and we can see that the 1 over x is going to go to 0, and the -1 over x goes to 0, and so does the 1 over x. And so we get by the sandwich theorem or squeeze theorem that that's going to get squeezed and have to go to 0 as well. All right, let's go to the next panel. And we have some more examples here. So here we have the limit as x goes to infinity. So it is okay to split this fraction up if that helps, and think of that as 5x over x plus sine x over x. Now as x goes to infinity, we can see that the 5x over x is going to go to 1. We just said that the sine x over x is going to go to 0, and so this will go to 1 plus 0, or 1. Next one's really interesting. This is one we'll see quite a bit in here. So first, as x goes to positive infinity, let's think about what happens. As x gets really, really big in the positive direction, it's going to get multiplied by a negative, so that's going to make that be a very large negative number. E to a large negative is, remember, 1 over e to a large positive, and as that gets really, really big, this term is going to go to 0 and drag that 9 with it. So this will look like 10 over 2 plus 0, which is 10 over 2, which is 5. So our limit as x goes to infinity there is 5. This will have a horizontal asymptote to the right of y equals 5. So that's our horizontal asymptote. Now, meanwhile, if we go to negative infinity, now if x is negative, a large negative times a negative makes that a large positive. E to a very large positive gets really big. Times 9 is bigger still, plus 2. This is going to be 10 over a huge number, so that is going to approach 0. And so we will have y equals 0 is going to be a horizontal asymptote to the left. So this has a different horizontal asymptote to the left than it does from the right. Now we can talk about limits as we approach a from one side or the other. So as we plug in numbers that, so I didn't want to say a, that I meant that to be limit as x approaches 0 from the left of 1 over x squared. So as you plug in a very small negative number, it's going to get squared and become positive, but still very, very small. And so 1 divided by a very small number gets very, very large. We could say positive infinity, or you could also say it does not exist. In this case, the positive infinity is a little more descriptive about what's happening with the graph. This also was intended to be 0 from the right. So if we plug in a very small positive number, again, the squaring is going to keep it positive. In a similar fashion, this also is going to go to positive infinity, or we could say it does not exist. As we approach 2 from the left, like if you're plugging in 1.9, 1.99, you're going to get 1 divided by a very small negative number, which is going to make that go to negative infinity, or we could say the limit doesn't exist. And plugging into, approaching 2 from the right, like 2.1, 2.001, then this is going to be 1 over a very small positive, so that's going to go to positive infinity or does not exist. So we get here then our definition of what we mean by a vertical asymptote. So if our one-sided limit on either side goes to either positive or negative infinity, that qualifies as a vertical asymptote. So we've seen examples here of some like the 1 over x squared, where it goes to the same infinity on both sides, and in the case of 1 over x, It goes to positive infinity on one side, negative infinity on the other. Just for the record, it would be a very strange one, but it would conceivably be possible to have something like, maybe it approaches, some finite number on the right, but still blows up and goes to positive infinity or negative infinity on the left. That still would be considered a vertical asymptote. All right, very good.